Okay, so just to refresh everybody, when we talk about Le Chatelier's principle, Le Chatelier's principle is based on the principle of saying what is done must be undone. So if you add something to a reaction, you need to get rid of it. If you remove something, you want to go and you want to create it again. So if you remove a product, you're going to want to form that product again, and then equilibrium will shift to create more products. If I were to remove a reactant, then I would want to shift to the reactant side to recreate that reactant. Same thing, if I add something, I want to get rid of it. So if I were to add a product, I'm going to shift to the reactant side to get rid of it. Whatever's done must be undone. So when we talk about solubility, if your compound, if there's anything in the compound that can react to an acid or base, pH has an impact on whether it's more soluble or less soluble in that solution. So if you have an ion in a compound, an ionic compound, and one of those things can react to an acid or base, that can influence how soluble this compound is. So if I'm looking at this reaction, when I dissolve iron hydroxide, I'm going to create the hydroxide ion. Well, creating that hydroxide ion, well, I know this is a base. Bases react to acids. So if I were to add an acid to this, so if I were to add some H+, I'm going to react that out and I'm going to create water. So if I've reacted the hydroxide out, I've essentially removed it from the system. If I remove something from the system, I want to replace it again. It's going to shift to the product side, and we're going to dissolve more of this iron hydroxide. So when you add an acid or base, if one of those ions can react, it's going to shift the equilibrium. So would the pH, okay, so what pH would mean that this compound would be more soluble? So would it be an acidic solution or a basic solution? Well, if I have an acid, it's going to react to that hydroxide and then pull it out, so it's going to make more of this dissolve. So an acidic pH. So what would happen to the solubility if you added a base? Well, if I added the hydroxide, so if I add a product, I want to get rid of the product, which means it's going to shift to the reactant side. So the solubility would decrease because I'm going to make more of that solid. Okay, so let's look at this particular reaction. I have silver acetate and it's dissolving to make silver ions and acetate ions. So first thing, if I have an acid to this, will the acid react to either of these components? Okay, well, I now have acetate. And I know acetate, if it has an acid present, it will react with that H+ to create acetic acid, which is a weak acid, which means it's a little more likely to stay intact. So if I were to add the acid, it's going to react to the acetate. So that pulls it out of the solution, which means if I pull it out, I want to make more. So it's going to drive it to the product side. It's going to make this more soluble. So once you know if your acid is going to react, well, if you add a base and you have a pH that's higher, that's going to do the opposite effect. It's going to decrease the solubility here. Okay, so which of the following pHs would I expect the iron hydroxide to be more soluble? Well, iron hydroxide produces hydroxide, and hydroxide is a base which reacts to an acid. So the most where the solution with the most acid is going to be the one with the lowest pH. So it should be more soluble in the 4.5. And then if I had 2 as an option, that would be my best choice. So my lowest pH possible would make it more soluble. Okay, so if the solubility of iron hydroxide, what is the solubility in a solution of a pH of 9? Okay, so if I have a pH of 9, okay, that means that it's a basic solution. Bases have hydroxide in them. So the first thing I need to do, I need to calculate how much hydroxide is present. And this would be very similar to the common ion effect. So I know my pH is 9, so my pOH would be equal to 5. So that means my hydroxide concentration in this particular solution would be 1.0 times 10 to the negative 5. And just remember, this is a pOH equation, or a calculation, so pOH is equal to the negative log of the concentration of hydroxide. Divide by -1, do the anti-log, and then you should get this. Okay, so the solubility, we want to find the solubility. So what we're going to do, we are going to set up an ice table. So here's my lead hydroxide. Okay, so now I'm going to make my lead ion, and then I'm also going to make 2 hydroxide ions. Watch for those coefficients. Okay, so don't care about that. Lead would be 0, but my hydroxide concentration is going to be different. It's 1.0 times 10 to the negative 5th. So I'm still adding x here, but here I'm adding 2x. So I get x, and then I get 1.0 times 10 to the negative 5th plus 2x. Well, KSP is very, very small here, which means I can assume that x, when it's being added to a number, is almost 0. So I can get rid of that. So my KSP is going to be equal to my lead multiplied by my hydroxide squared. Don't forget that. That's why we look to write things out. So my KSP is equal to 1.2 times 10 to the negative 15th, which is equal to x multiplied by 1.0 times 10 to the negative 5th, and we leave out that 2x because of the fact that it is negligible. We can approximate. Don't forget to square it though. For x here, I'm going to get 0.0000012. That's my molar solubility. So I can dissolve 0.0000012 moles in 1 liter of a solution that has a pH of 9.